Yeah, hello, my name is Jan Brugård. I'm the CEO of Wolfram MathCore, developers of System Modeler, and today my colleague Nico Eroesco will present the new aircraft library that allows you to model aircraft as a conceptual level in System Modeler.
Yeah, so hello everyone. My name is Nico Eroesco, and I work as an applications engineer also at Wolfram MathCore, and I will be giving you this presentation from Sweden about aircraft design in System Modeler. When a new aircraft design is designed and eventually being manufactured, its design and manufacturing is nowadays pretty much spread out throughout the world to a bunch of different subcontractors. So the question is, how can the aircraft design be tested as a whole aircraft throughout these design stages? So roughly a year ago, we partnered with Saab Aeronautics to develop this aircraft modeling library that will make it possible to test an aircraft at the early aircraft conceptual design stage. I will start by pointing out one key variable in aircraft design, which is the aircraft's weight, and then why are the aircraft designers and the airlines especially obsessed about it. Why do they want to find ways to reduce aircraft weight, and then why do they charge ridiculous amounts for excess or overweight baggages and so on. So here we used the library to simulate an example for Boeing 737-800 for 3-hour, 15-minute flights with different fueling levels ranging from 5 metric tons to close to the fuel capacity limit of that aircraft in 20 metric tons. And we see that with the lowest fueling level, we pretty much run out of fuel at the end of the flight, whereas with 20,000 kilos, we still have close to 15 tons of surplus weight at the end of the flight. But the interesting thing here to note is how all this affects in the fuel consumption itself. So here, like said, when fueling up to 5,000 kilos, the fuel consumption is all of that. Whereas with the highest initial fuel mass, we get up to 6,200 kilos. So it's an increase of 1,200 kilos, or roughly 3,000 pounds. And yeah, this was just to demonstrate how just the fuel mass itself will affect on the fuel consumption. But should the weight reduction be done somewhere else, for example, in making the fuselage out of lighter materials, that would perhaps correspond to the weight reduction of these 15,000 kilos, then that would of course lead to a fuel consumption reduction of this magnitude. And then on top of that, then of course we could fuel the aircraft with less fuel due to this weight reduction in its dry mass, and then have a further reduction in fuel consumption. So therefore, whenever a method for a method for reducing weight somewhere in the aircraft, it will lead into this positive loop that is desirable. And also this is very good, or this is why it is also extremely beneficial to have efficient engines that will consume as little fuel as possible. Then I will move on to the actual simulating or modeling of the aircraft or its motion through air. And for that, we need a flight mechanics model of some sort. And the Wolfram system modeler with the physical modeling environment is a quite powerful tool for doing so, for the reasons that we can, for instance, apply the aerodynamic forces locally on the surfaces of the aircraft. Here we see the lift force acting on each side of the aircraft wings, similarly to the drag, and the negative lift on the horizontal tail to pitch up the aircraft to get it into the trimmed condition. And at this very time instant, it is also or has deflected the ailerons such that it would start to rotate left. And together with those forces, as we get also the forces and torques that are due to the mass, center of gravity, and moments of inertia of the aircraft, we actually can quite well build up 6 degrees of freedom flight mechanics model to model the movement of the air, or the movement of the aircraft through air. Then we might think, why is it a good idea to involve this kind of 6 degrees of freedom flight mechanics model with simulation capability in aircraft conceptual design? Firstly, it comes down to the output of the model, that is the flight trajectory. So it gives us the opportunity to assign pretty much whatever flight mission we want to for the aircraft design, and then analyze its performance for that specific flight mission. And also that all that can be done within one single tool, where we can input those parameters that we actually know at the aircraft conceptual design stage, and then those will be further used to estimate those parameters that are required to actually simulate the flight of an aircraft. Then a bit more closely on how the library works, or how the different domains works there. Firstly, I will present the one key component there, that is the autopilot, and that is used to translate the variables that we use to describe the flight mission, that are the altitude, flight speed, and drag angle at any given time instance. And the autopilot will translate those into the control actuator commands that are the throttle position for the engines to control the velocity, ailerons to control the roll angle, elevator to control the pitch angle, rudder to control the yaw angle. And these are the inputs that then can be entered into the flight mechanics model, and then eventually we get the flight trajectory as the output, and from which we, of course, need to send feedback back again to the autopilot. Then, when it comes to entering the parameters of the aircraft into the library, like I said earlier, in the early aircraft conceptual design stage, a lot of the variables are still unknown. Most importantly, the total lift and drag coefficients, and the aircraft mass, center of gravity, and moments of inertia. So here in this library, we use a bunch of different empirical relationships found in the literature to estimate those values from those parameters that are easier to establish, that we usually know at the aircraft conceptual design stage. Then when we look more closely how the aerodynamic properties are estimated in the library. So for that, the inputs from the aircraft are the properties of the two-dimensional airfoils used in the different wings or surfaces that are the main wing, the tail. So those values, they are rather easy to get into. There are a bunch of different table values for different airfoil shapes in existence that are easy to get into. And then we need some key dimensions of the aircraft or from the aircraft geometry. We need things such as the wingspan, the width and height, and the length of the fuselage, the dimensions of the tail and their positions, and so on. And then together with the embedded model for the atmosphere, we get the actual Mach number and the Reynolds number locally on each surface or on each component. And together with all these inputs, we can establish by using correct empirical relationships to estimate the aerodynamic coefficients of the entire aircraft, such that the air compressibility effects are also considered. Then when we move on to estimating the mass properties, there on top of the aircraft geometry, we need some design variables of the aircraft design that are, for example, the number of passengers, to design cruise Mach number, whether we use composite materials or not, and so on. And then some properties of the engines. And with all those, we derive the so-called dry mass properties that are the mass center of gravity location and moments of inertia, such that we consider the tanks to be empty. So those properties are constant over time. And then the tank dimensions, they're also derived from the aircraft geometry, more specifically the fuselage and wing geometries, and then how the fuel is burned from there. There we use the engine model that also takes input from the atmosphere model to calculate the fuel burn rate, and eventually we get the variable mass properties to get the mass, the center of gravity location, and moments of inertia of the entire aircraft as a function of time as the fuel gets burned inside the tanks. Then the library also includes options to model aircraft with electric powertrain. Then, of course, all this becomes much more simpler as everything stays or remains constant. And then should any mass property of any component be known exactly, then we can just bypass the equations for estimating that value and then just enter the known values. And that is most likely usually the case for the engines. We can choose some certain engine and then just enter its mass properties there into the model instead of estimating them. And then, as we showed earlier, where we simulated the flight of Boeing 737, we can also simulate the flight of existing aircraft just by entering the mass properties of the aircraft as a whole into the model, thus not requiring any estimations on those properties at all. Then a short example again on how we quickly redesigned this old Boeing 757-300, which is an old narrow-body medium-range aircraft. So we resized that such that we would use these newer, lighter composite materials instead of aluminum alloys. For doing that, we entered the design variables of this aircraft as such to the model, with the exception of course, where we changed the parameter to state that we actually use the composite materials in the structures. And this is just one Boolean parameter that will then apply the correct weight reduction factors in the correct equations to represent the consequent weight reductions once we use those materials. Then, of course, we want to assign some flight mission to test how the a new aircraft design manages that, and for that we used the actual flight data of a real flight, transatlantic flight from New York to London, and further from London to Amsterdam. And that was for simulating a flight to a diversion airport after a missed landing approach. And this is something what the airworthiness authorities require, that on each flight we need to have fuel for this sort of scenario. So these flight data were pretty much able to be entered just as such as the commands to the autopilot, and then we could evaluate the aircraft for this given flight mission. But it wasn't not that easy just to play start and see what the mass becomes, but actually the aircraft sizing is an iterative process all in all. So there are these 4 points we need to go through. Firstly, size the engines that we have enough thrust, but not too much, so that the engines are not too heavy. And then same goes for the tanks, that we have adequate amount of fuel for the flight mission. And then actually one of the design variables that is entered to the model is this sort of initial guess on the design maximum takeoff mass. So that will be readjusted such that it will eventually converge with its estimated counterpart. And lastly, we need to check that none of the constraints set on the load factor or maximum dynamic pressure that are also some of the design variables entered to the model, that they are not violated. And if they are, then of course we need to readjust them, which will then lead to changes in the aircraft mass. And then we need to do a lot of the things all over again. So this just to demonstrate that it actually is iterative process to go through all this. But eventually, when everything here was done, we were able to reduce the maximum takeoff mass of the Boeing 757-300 by 37 metric tons, or about 82,000 pounds. And one can imagine what this kind of reduction in the structural weight will then, especially in the long run, have an effect in the fuel consumption of an aircraft. I will conclude by these few points on the aircraft library. So bringing this kind of 6 degrees of freedom flight mechanics model into aircraft conceptual design is a valuable addition, as we can validate the performance of the aircraft design on such an early design stage. And it also enables working with multiple disciplines with one single tool in one language, or two if we go on to Mathematica. And the modularity of the library enables that in the future we can add more disciplines to the model, such as aeroelasticity, turbulence, etc., or to enhance the fidelity of the existing disciplines. But with this, I will thank you all for participating and listening. And I think we move on to questions.
So Nico, see, is this on?
Yeah, I can hear you.
Yeah. So I have a couple of questions. You haven't shown the actual library. Can you show the actual library and the simulation, so people actually see it flying?
Yeah, of course. Yeah, I can do that. I will drag. Luckily, I have here something open. So here we have, for example, this one scenario. Actually, I will show it on the model center first. So we have this one scenario, because what is amazing about the physical modeling, or this environment, that we can put multiple aircrafts in one scenario. Here we have, for example, an electric aircraft towing and glider aircraft up into the air. So if we move on to simulation center.
That's my fault, I have to admit. I think because you're using Nextcloud and I moved some stuff there, so that's my fault.
Okay, but that's
but I hopefully have it. Let's see if I continue and I'll see if I fix it on my computer.
Yeah, as a backup, I can simulate something where we don't use those CAD files. That would be this example.
Anyways, while he's resimulating here, I'm doing the same. Any questions on either this or the green energy, and we'll happy to answer. No questions? Then I can point out a couple of more things about this. This library that you see here is come out soon. It will be a free library for System Modeler. It has been developed together with Saab Aircraft in Linköping. They're based in the same city as us. They develop fighter aircrafts, and the reason why they are part of this is because they want to use it particularly for this conceptual design, so they can early on. The problem is that for them early on in the process, they want to test the subsystem, and they have no real good method for that. With this sort of thing, they could get this model and then plug in some more detailed model of whatever their system is, and test that and see how it will work. And you can also, if you want, later on downstairs at the basement, we have it set up so you will be able to fly it and actually play around with the joystick to have it. I have it up and running here, because so I can take the screen share.
Okay, perfect.
Yeah. Hopefully, there you go, screen share. So this is now you see here the electrical aircraft, the Pipistrel. Sorry. Oh, and is it not? It says that I'm sharing here. So that's odd. Oh, there you go. It was just slow on updating. So we have the Pipistrel electrical aircraft here, and we have a glider aircraft. So this aircraft is a few years since this was developed, while the glider, I think, is from the 70s. And let's just play around with it here. We can see, can zoom out a bit. We see their flight paths. Right now, of course, the glider will just try to follow. It's attached here with some rope, and we'll try to follow to create a small force as possible in between them when flying. And let's just skip forward a bit and increase the speed, let's say to 5 times perhaps. There you go. And eventually we'll see at which time is it
around 800 seconds.
800 seconds. So let's skip forward a bit. Oh, let's do this. Hopefully. Yeah, now it should be, there you go. And now it's flying on itself. And it drops down. Of course, they want to drop down to different levels here, not to crash. And now the 2 aircrafts are flying on their own. And of course, yes, that's for the other aircraft here. You can test different designs for the glider. What happens if you have a shorter wingspan, longer wingspan, and so on. And if you want to try this and fly it with a joystick and connect it to a nicer simulator environment or visual environment, so you can fly it for Champaign or Linköping, welcome to the basement. Thank you. Or any questions before we wrap up? I don't remember the average transmission loss, but we can check that. Or perhaps you have it. Remember it, Ankit?
It's usually like 10% is the like transmission loss usually, but in our simplified model we have I think
It will
it's
depend
like,
on the length of it.
yeah,
Well, we can see
it depends
here.
on the length. Yeah.
Transmission current, yeah. So here we see the voltage drop from voltage out and in. So that basically is the loss we see there over the transmission line. And well, that actually looks like to start 300, and it's so it's about 5%, something like that, slightly less in this case. And the transmission lines are not really detailed model here. There is a presentation coming up. Perhaps that's you. I don't know. Coming up later today, I think, right? It's 4:30. This one, model transformation for smart grid applications, and that will be more detailed and have more concrete answers on that, I think, right? He's hoping. Yeah, then thank you very much. And please visit other system modeler sessions during the conference.